Thank you very much for having me. I appreciate that. It's always fun to give these talks, and I love talking about serverless. So today we're going to talk about how to fail with serverless, and we'll get into some of the details of what I mean by that. But first, just to introduce myself, my name is Jeremy Daly. I am the CTO at AlertMe.News. It's a small company out of New York City, although I do work remotely just outside of Boston in Massachusetts. I've been consulting with companies for quite some time. I've been a veteran of technology startups, so I have gray in my beard and in my hair, and that is real, plus the fact that I have two daughters, one who's 12 and the other who's 14, that helps to contribute to my gray hair problem. I started working with Lambda or with AWS very, very early, about 2009, with all the fun VMs and all that stuff and EC2 instances, and then started using Lambda in 2015. I blog at jeremydaly.com. I do quite a few open source projects. I do some speaking. You mentioned the Off by None newsletter that I write every week, and the Serverless Chats video podcast. It's now a video podcast, so check that out on YouTube or on any of your favorite podcast apps. And I'm a AWS Serverless Hero, which is a really great honor. It's a really great program if anybody is doing stuff in the serverless space and you want to sort of get some insights into what AWS is doing and get a little bit of a head start on when they start releasing new products and being part of the beta testing groups and being able to provide feedback and stuff. It's a really great program, so something you could definitely check out. All right, so have a kind of busy agenda today. I hope to get through this in about 45 minutes and leave some time for questions. But we're going to start by talking about distributed systems and serverless. Then we will get into writing code for the cloud. We will talk about failure modes in the cloud. We'll go through a few serverless patterns to deal with failure. And finally, we'll talk about decoupling our services. So distributed systems, if you're not familiar with distributed systems, essentially what they are is just a bunch of networked systems that need to communicate or coordinate with one another by passing messages back and forth. The other thing that is important to note about distributed systems is the fact that they are really, really hard. So anybody who's building distributed systems and tells you that they are not hard, unfortunately, they're not telling you the truth, because it is a difficult thing to build. And part of that reason is because of something that this man says. If you're familiar with Werner Vogels, the CTO at Amazon.com, he essentially says that everything fails all the time. And if you're new to distributed computing or you're new to the cloud, oftentimes you will fall victim to what we call the 8 fallacies of distributed computing. So these 8 fallacies are things that in normal traditional systems we might take for granted or assume or make these assumptions. So the first one is that the network is reliable. We are communicating between multiple containers or serverless functions or different server full services, and the network fails all the time. We lose packets, things don't get routed correctly. So this one is not true. Latency is not 0. I'm over here in Massachusetts. Probably most of you are watching this somewhere in the UK, and that is a problem because we have a speed of light problem. So latency is never 0. You always have to deal with some bit of latency when you're transferring messages between multiple systems. Bandwidth is not infinite. They can only get so much light can travel over a fiber optic cable. The network is not secure. It may be secure when you generate something, but it's easy or it's possible for someone else to put some other packets on your network, so you can't always trust everything that is broadcast across your network. The topology of a network changes all the time. It's being rerouted. It reroutes based on latency, based on other factors. Something goes down, so you can never necessarily trust that something is always going to be in the same place. There's always more than one administrator. Transport cost is expensive, and the network is never the same, so you're always dealing with different things across that network. So serverless applications, when it relates to distributed systems, are essentially distributed systems on steroids, right? And that's because they're smaller, they're more distributed compute units, they're stateless. So in order to rehydrate any type of state, we need network access in order to do that. They're highly uncoordinated. So if you think of being able to communicate between Lambda functions, for example, you need to use buses or queues or state machines or something to coordinate that behavior. And they're really reliant on networked cloud services, right? We're not writing databases within a Lambda function. We're relying on RDS or some other service to do that. We're not writing our own queues. We're relying on other services to be able to use those. So this, I think, is an AWS meetup group, but I'm sure most of you are probably a little bit familiar with serverless. So when you talk about serverless, you hear about serverless, oftentimes we hear things like, oh, there's no server management, the flexible scaling, you only pay for value, or you never pay for idle, and automated high availability. And those are all true, but one thing that we don't necessarily talk about, in terms of what it means to be serverless is the fact that it is a lot of configuration and a really deep knowledge of all the other cloud services that are available out there. So you need to know that stuff. And the other thing is that serverless really just falls into this event-driven paradigm, which for many people, for many developers, this is sort of a new concept. So in the AWS ecosystem, we're talking about sending messages back and forth and doing all this communication. There are a lot of services that we need to communicate with, right? So we have a sort of subset of services that people like to call serverless, and these are things like Kinesis or DynamoDB or SQSQs or AppSync, things that really we don't have to worry about scaling. We don't have to worry about provisioning a certain amount of capacity. That just sort of kind of takes care of itself for us. Then we have another category that, sort of this managed services category. And these are things like, maybe Elasticsearch or Redshift or RDS, Fargate, things like that, where the management is handled for you, but you do have to think about the scaling characteristics of these, and you do have to sort of, be conscious of these as you're scaling up. And then finally, we have these non-serverless things, and this is essentially anything that runs on EC2 or Docker or Kubernetes or Kafka or things like that that are running that you have to actually manage the underlying the underlying infrastructure for if it's running on something like a VM. But the point is that there are a lot of different services that have to be connected here, and so. From a traditional standpoint, if we think about maybe ops people or even DevOps as we sort of move to that, a lot of the thinking comes down to, or had come down to, this idea of reliability or high availability, which essentially means that we're trying to keep some level of operational performance, right? And that usually is measured by uptime. So how many nines can we get? 5 nines, 6 nines, 7 nines, whatever that is. And that works in a traditional system when it's a monolithic approach, and essentially if something goes down, the whole thing goes down and nothing, nothing runs. But as we move to distributed systems, and when we especially moving into the serverless paradigm, we need to start thinking more about resiliency. And what resiliency is it's not about not failing. It's about being able to absorb failure, right? So if there's some sort of problem in your system, you want to be able to absorb that and still provide some acceptable level of service to your customers. So it's not about preventing failure. It's really about understanding how to gracefully deal with that. All right, so now taking a traditional approach, right? We would write our code in sort of this monolithic fashion. We'd write these big huge apps that we would deploy as single units. But when we start moving to writing code for the cloud, things are going to be a little bit different. And one of the ways that we will write code in the cloud, especially for serverless, is by using functions as a service. So this would be using something like a Lambda function, for example. And this is going to contain our business logic. But this is much different than your traditional application because these are ephemeral compute services, which means that the code spins up, it runs the container spins up, it runs your code, and then it goes away. Sometimes you have warm starts, it'll already be live, and other times it'll go away. So you really can't store any state in these. It also runs your code in response to events. So this is that event-driven idea where it's not just sitting there running code in the background. It is waiting for something to happen that explicitly triggers it. It automatically manages that runtime, compute, and scaling, which is a really great feature, but also gives you, it takes away some control from you. Another important thing is that they're single concurrency models. So with a traditional, say, Node app or Python app, you might have multiple threads running that can respond to several requests at the same time. This is a single concurrency model, which means for every concurrent user connection that is activating this Lambda function or invoking this Lambda function, that it's going to actually spin up a new container for each one of these. And finally, this is something that I think people get confused with, even when it comes to just load balancing applications, is there's no such thing as sticky sessions, and there's no guaranteed lifespan in Lambda functions. So you can't guarantee that user A who hit Lambda function 1, 2, 3 is going to hit that same Lambda function again. They could get bounced around into different places. So you can't rely on global state to maintain some sort of session data when it comes to that. So when we write our traditional services or traditional code, typically the way that we would cover error handling and things like retries is that we would just use this beautiful try catch block, right? This has been a standard for quite some time. You do something important, it fails, and you might try logging that, to do some error handling in there and maybe some cleanup. Maybe you try doing some logging. Maybe you even try to retry the actual operation itself. But when you're using ephemeral compute in the cloud, you have to ask yourself the question, what happens to the original event, right? We're not just capturing all this stuff. So you have something that triggers this ephemeral thing that is going to go away. So you can maybe try logging that so that you have a copy of the original event. But what happens if there's a network issue? So most people think you just write to CloudWatch logs right from your Lambda function, and that data is automatically in CloudWatch logs. That's not actually true. There's actually an asynchronous process that runs in the background that eventually dumps that data into the logging system, which can fail. And if that fails, then those logs get lost. Also, what happens if the function container crashes? So this is possible. You have some bit of errant code or some sort of memory spike or something happens where the function or the container that holds this function actually crashes. Then it never even gets to your catch logic. So you can't do logging and you can't retry the operation. And then there's this other concept with Lambda functions that, it's possible that the function never runs. So you might try to call the function, it gets throttled, something happens where the function never actually runs. And so in all of these cases, we lose the events, and this is quite obvious, but losing events is very, very bad. So in order to understand partially why some of these things happen, right, we have to understand the different types of errors that we can get with a function. And so in Lambda functions, you have your traditional sort of exceptions or unhandled exception errors. These are great. In most cases, you're going to go ahead and catch some error in your code or something happened, and it's going to go ahead and throw that catch logic for you, and you're going to be able to handle something in there. But then you have function timeouts. So if your function is only set to run for 30 seconds and it takes 30 seconds to try to do something, that catch block is never going to run. Same thing's going to happen if you get an out of memory error, right? So you only have so much memory, that memory spikes, all of a sudden the function can't run anymore, that gets throttled, and next thing you know, your catch block didn't run and that data was lost. And then the same thing with throttling errors. So your Lambda function won't even try to run if you already have too many concurrent invocations of it based on your reserved concurrency setting. So it's possible that it'll never even trigger it. So an important thing to remember is, and this is a little tongue-in-cheek, but the cloud is better than you at things like error handling, at things like retrying failures, understanding network failures, mapping its own network topology, right? AWS knows much better than you which services are available that you're trying to connect to. And also for handling things like failover and redundancy. So it knows when something is not working correctly, it knows when a network path isn't responding, and it can handle that for you. So if the cloud is better than you at all these different things, you have to ask yourself the question, why wouldn't I just let the cloud do these things for me? And you can do this by what I call failing up the stack. So essentially what we don't want to do is we don't want to swallow errors with try catch statements. Instead, we actually want to fail the function. There's a caveat to this. Sometimes we don't want to do this, but for the vast majority of things, we do want to do this. And then what we do is we return those errors directly to whatever service is invoking our Lambda functions, and we can then use these retry mechanisms, these built-in retry mechanisms, to run all kinds of redrive policies. And then we want to make sure we take advantage of dead letter queues to capture failed events. We're going to talk about all this stuff in detail. So if you're not overly familiar with this stuff, we will get into it. But before we can understand how to fail a Lambda function, we actually have to understand the different types of Lambda functions. So I tend to break these up into 3 different types. The first one is what I call the Lambdalith and what other people call the Lambdalith. This is something that's a little bit scary. We're going to talk about these in detail. But this is something that is an easy on-ramp, but at the same time is not really good for using the cloud to capture these issues for us. The second one is called the Fat Lambda, which is actually an architectural design and is or an architectural choice in some cases, and can be very useful. And then finally, we have the single purpose function, which is something that we want to try to strive for. All right, so let's talk about the Mighty Lambdalith. This is the updated version of the monolith, the 2001 Space Odyssey. This is an ephemeral monolith, I guess. But essentially, what this does is it takes your entire application and you stick it into one Lambda function. Now, a Lambda function, for all intents and purposes, is just a mini Apache or a mini Linux server, not Apache, sorry, a mini Linux server that runs. That can run your code. So it's perfectly fine from a technical standpoint to put all the stuff into one Lambda function. And what we often see is these are people who are doing this lift and shift sort of thing, where they take their Express.js app or their Flask app or their Spring Boot app or something like that, and they just put it right into a Lambda function, and everything runs in one system. Now, oftentimes these types of applications are always synchronous, so you're connecting to them via the API gateway or like an application load balancer. And the biggest problem with these is that partial failures, it couldn't connect to the database, it couldn't do something here, those actually are handled in the code. And we just talked about all the reasons why trying to handle errors in your code or failures in your code can be a problem, because we're not necessarily going to catch all of them. So the next one is the Fat Lambda. This is where you take several related methods and you co-locate them into a single Lambda function. And oftentimes this is used because what you want to do is you want to increase the speed of some sort of synchronous operation. The team over at Lego does things like this in their checkout process. Bustle does things like this in order to do some rendering and things like that. So there are plenty of use cases for this. The partial failures are still handled in the code, but under the right circumstances, this can actually be a really powerful and useful approach, right? Because if you're doing it purposefully and you know what you're trying to accomplish, this can actually be a much more efficient way of connecting functions together, as opposed to trying to do something like some complex function composition, or even worse, synchronous communication between functions, and trying to sort of couple things like that. So then the final one is the single purpose function. And this is essentially just a tightly scoped function. It handles a single discrete piece of business logic. These can be invoked synchronously or asynchronously. And any failures in this context would be total failures, right? So if the function fails because the only thing it does is write something to the database, if that fails, I can fail the entire function, and I don't have to worry about other side effects that I might have to go and clean up. And these then can get passed back to that invoking service. So what's great about this is that these functions can be reused as part of other workflows. You can scale or throttle them independently, which is important. So you may have something that needs to scale really, really quickly. You may have something that doesn't scale quickly because maybe you have a dependent downstream system that can't handle that scaling. And then the best part of these things is that you can use the principle of least privilege. And if you're unfamiliar with that, essentially what that says is if my snippet of code only needs to read data from this table in a database, then that function should only have the permissions to do that. And that's really great for kind of putting up those bulkheads and minimizing that blast radius. If anything ever got compromised, great, but also just being smart and making sure there's a little bit of extra safety there. All right, so let's get into failure modes in the cloud. There is a ton of information that I'm going to throw here. I know this is being recorded, and so maybe this will be more helpful as something to look back on. I don't expect anybody to absorb everything that I'm going to tell you now. It's going to read a little bit like documentation, but it's important because there are just so many different things that are happening in the cloud that that knowing, or at least having a general idea, and hopefully this will stick in your brain. You'll say, oh, that's right, it happens differently with async or synchronous. So hopefully this will just give you a good background and allow you to dive into the docs and figure out the exact the exact scenarios for your code. So the first thing we need to do, though, is quickly talk about retries. In distributed systems, as we said, the network fails all the time, so retries are a very vital part. If we tried everything only once, then that would pretty much, kill half of our application, or I don't know if it'd be that much, but part of our applications would lose a lot of events that way. So most cloud services in AWS will guarantee what's called at least once delivery. This is great, meaning that you're almost guaranteed to make sure that your function or your SQSQ or whatever it is gets called at least one time. But it's also possible that it could get called more than once with the same exact event. So this is something where we have to be conscious of anything that can retry operations, which is pretty much any type of system in AWS. You want to be careful and make sure you accommodate, or you think about idempotency. And if you're unfamiliar with idempotency, essentially what this is this concept that an action or some sort of event would be idempotent if it can be repeated multiple times and there's no side effects. So if you think about functional programming and pure functions, you send the same input, you always get the same output. And so something that would be, sort of a example of this would be if I update a database record. So if I send the same data into a database record, that is going to have the same effect on the database, most likely, other than maybe like the modified date. I can authenticate a user 1,000 times and I should always get the same information back. I can also, if I'm updating a record in the database, I can check if it exists. If it exists, then I don't do anything. If it doesn't exist, then I would create it. So there are a lot of strategies around idempotency, and that's definitely something that, when you're building these systems, be aware that distributed systems will likely get duplicate events every once in a while. Doesn't happen often, but it does happen. And if there's something like, say, charging your credit card twice, we don't want that to happen. So just things to think about. And then dead letter queues, we talked about these quickly earlier, but essentially what dead letter queues are is they're these systems that allow you to capture messages and events if they fail or are skipped. And we'll talk about what skipped means, because it is possible to skip and not necessarily fail messages. These are great because they allow you to do things like inspect the data. You can set alarms on them when they get too many messages in them, and often tied to queues. And you can potentially replay those events if there is something that that just failed because maybe it was a downstream issue or something like that. You can add dead letter queues to SQS queues, to SNS subscriptions, and also to Lambda functions, which is very handy. So then the other thing that we need to think about too, because this is where some of these failure modes come in, is that depending on how a Lambda function is invoked, has a big impact on how the retries work. So there's a couple different invocation types for Lambda. You have your typical synchronous Lambda invocations. This is that request response model. You have asynchronous, which is that idea of set it and forget it, and it's sort of a queue-based system. You have stream-based, which pushes data into Lambda functions, and then you have polar-based, which will pull data and execute a Lambda function or invoke a Lambda function with that. So I want to get into the retry behavior of each one of these because they are all different. And again, don't expect you to remember all this, but just sort of maybe it'll tickle something in the back of your brain when you're thinking about doing these things. So as we said, these are invoked using a request response method. Failures here would be returned back to the invoker, right? And so again, if you catch that error in your code and you don't return an error, then it would just assume that it worked correctly. So we don't want to do that. Instead, we want to fail that function, bubble that error up, and that actually gets returned to whatever the invoking service is. Any retries would be delegated to the invoking application. So there are some applications or some services that would automatically retry. So Alexa and Cognito, for example, if you invoke an Alexa skill, it'll try your function. If that fails, it'll actually try it a couple more times. And the same thing with Cognito. If it's trying to authorize against a function, for example, it would try that multiple times. However, most services don't. So something like API Gateway and step functions, if the Lambda function fails, it will not automatically retry it. Instead, it will pass it back to that service. And certain services like API Gateway and ALB, these sort of user-facing ones, will actually return that client, return the error back to the client, so that your web browser or whatever your logic you've written on your local application and your mobile app, whatever, can actually determine whether or not you want to issue a retry there. So the next one is asynchronous Lambda retries. So there's actually a Lambda service that runs between asynchronous invocations of your Lambda function, so that when you submit an event to the Lambda service, it'll take it and it adds it to a queue. And the way that this works is that it'll add it to the queue and say, okay, I've received the Lambda function, received the event, and then it will just send a 202 back to whatever that invoker was and disconnect. So now your invoking service does not know what's happening to that event, only that it has been queued and ready to be processed by a downstream Lambda function. So the Lambda function service, or the Lambda service, will attempt to reprocess this event up to 2 separate times, and you can change that with the maximum retry attempts. It's a new thing that was added at the end of last year. So essentially, this is one of those maybe delivered more than once type things. So it could actually run your function, and if you've got a whole bunch of code that's happening in there that maybe updates a database and then calls an API and then does something else, and then it fails at the end, the Lambda function is going to retry that up to 2 times. So essentially, you could be resubmitting that API call or whatever it is multiple times. That's why we need to think about idempotency, and why we want to make sure that our Lambda functions just do sort of one discrete piece of business logic. The other thing is that there's built-in throttling here. So if for some reason you have a function concurrency set on your Lambda function, and you sort of flood that with a bunch of asynchronous messages, it'll actually queue those for you and retry those for up to 6 hours, and that's something that's configurable as well. So you can use the maximum event age in seconds to configure that. And then finally, failed and expired events. So if the event fails more than 2 times, or whatever the maximum retry attempts is, or it expires after the 6 hours, or whatever you set for the age in seconds, it can be sent either to a dead letter queue or to an on failure destination. We'll talk more about on failure and Lambda destinations in a few minutes. All right, so then there's stream-based Lambda retry behavior. Essentially, records get pushed to Lambda function. It invokes the function synchronously, but it is handled by the stream itself. So Kinesis or DynamoDB sends them in batches, and there's this setting called maximum retry attempts, which I think defaults to 10,000, or defaults to it does up to 10,000. Essentially, if you have one bad message in your Kinesis stream or in your DynamoDB stream, that'll fail that entire batch, and that'll keep retrying. And by default, I think it's 10,000 times. It's definitely up to 10,000 times. So that's just something to be careful of, because you can just keep on retrying and retrying and retrying, and that's not the best way to handle that. So be careful of those poison pills. Oops, I'm going the wrong way. So there's another setting called maximum record age in seconds. That'll store records for up to 7 days, and you can change that. So essentially, if you have a bunch of old messages in there that aren't being processed for some reason, you can age those out, and that's where some of that skipping behavior comes into play. And then there's a new thing that was added called bisect batch on function error. So this is specifically designed to handle that poison pill issue. So if I send a batch of 100 Kinesis records into a Lambda function and it fails, rather than taking that 100 record, that 100 records or that batch of 100 records and just retrying that over and over again, it'll split it into 50 and 50. And then let's say the first 50 succeeds, but then the second 50 fails. Well, that'll split that into 25 and 25. And then I'll keep doing that process until it willows it down to the one message that doesn't, that's causing the problem, and then it'll take that message and go ahead and push that into your on failure. And so skipped records or failed records would be sent to this on failure destination, and that can be either an SQSQ or an SNSQ. So polar-based. So polar-based lambdas, those are actually a really, really great thing. This was added somewhere in the middle of 2018. But essentially, there's a Lambda polar service that will pull records synchronously from SQS in batches of up to 10. There is no bisecting here, so anytime a batch fails, it will fail the entire batch, but it is only 10 records, so it's not that bad. The max receive count is this setting on the actual SQS queue itself that will determine the redrive policy. I'll talk about that in a minute, but essentially this is the number of times that message can be returned to the queue before it triggers the DLQ, and that can be up to 1,000. The polling frequency is tied to the concurrency. This confuses a lot of people because they'll set the concurrency to 1, and then they'll wonder why so many of their SQS messages get redriven or sent to the redrive policy. There is a minimum concurrency that you need to set, and you can go as low as 5. You typically want to go higher than that. And there's some tweaks where you have to set the visibility timeout to at least 6 times the timeout configured for your function. So if your function times out in 30 seconds, then you've got to set your Lambda your visibility timeout higher than that, and so forth. So there's just a couple of little caveats. If you set this up right and you follow the documentation, it's well documented. It works perfectly, and this is great for again just using a Lambda function to consume messages off of a queue. So Lambda destinations, we mentioned these earlier. They are only for asynchronous invocations. So you can't use them on synchronous invocations, and they only work. So they don't work on things like like streaming or on polar-based lambdas. What's great about these is that you can do routing based off of whether the function succeeds or it fails. So if you think about your common asynchronous use case, it would be to capture some event, maybe put it into an SQS queue, or you're maybe reading something somewhere else. You want to be able to process that and maybe do something with it. And the solution to that would be, okay, I've processed this order, now I got to go update the database, or now I got to go notify a bunch of subscribers that this action was completed. What you had to do in the past was you had to actually write code in your Lambda function. And again, the cloud's better than you at doing that. So you could oftentimes lose some sort of an event because that succeeded in terms of doing the operation you wanted, but it failed when trying to send that message to EventBridge or to SNS or something like that. So now with this on success routing, you can actually just have that automatically route that for you, and it will send it to whatever service you have configured. And it will also do the failure modes for this. And the on failure destination should actually be favored over standard DLQ. If you're still using DLQs on asynchronous functions, that's perfectly fine. But on failure is sort of the new standard for doing this. And part of the reason is because it captures the context. So you will get information about why it failed. You'll get the stack trace and some other information around that. So destinations can be sent to SQS, SNS, Lambda functions, and EventBridge, which is pretty cool because then there's a lot of really cool patterns you can do with that. I'll show you one before we finish here. The other thing about destinations is they're specific. Their JSON is specific to where you're sending it to. So if you're sending it to SQS or SNS, it'll just be passed as the message. Lambda functions accepted as the payload. EventBridge, it goes in the detail, and the source is Lambda with a lowercase l, whereas anything else from Lambda has a capital L. I don't know why that's the case. The detail type will be obvious to know if it's a success or a failure, and you'll get some information about the ARNs, which you can use as well for your logging or your redrives. So speaking of redrives, SQS redrive policies essentially allow you to say, if I'm pulling data off of an SQS and I keep putting data back onto it or keep putting the message back onto it, then eventually I'll be able to send those to another SQS. That's where that maximum receive value comes in that we talked about for that polar system. For SNS, this is new in terms of dead letter queues, so you can now attach those to the subscriptions, not the topics themselves. So with subscriptions, if you're maybe calling a Lambda function with an SNS trigger, or maybe your HTTP or something like that, you've got a couple different sort of small or I guess not massive distributions, then these kind of make sense. If you are doing it for 100,000 APN calls or 100,000 SMS messages, I don't think you would want to put dead letter queues on each one of those. It only supports SQS, so you can't send SNS back to SNS for a DLQ. And then for certain things, it will not retry. So like if a Lambda function doesn't exist. And here's an interesting sort of factoid. When you send a message from SNS to SQS or to Lambda, it gets retried over 100,000 times for up to 23 days. So if for some reason the zombie apocalypse comes and we're all wiped out, then your SQS or your SNS messages will still be delivered to SQS, so you can have that peace of mind at least. Other messages like to SMTP, SMS, and mobile, there's retry 50 times over 6 hours. Again, I don't know why all these things are different. That's just how it is. And then if you're using HTTP endpoints, you can actually do custom defined policies. So this is great because you can say, I want to try this endpoint 10 times, and I wanted to, delay, 10 minutes between each one, or 30 seconds between each one, and you can set your back off strategy to like linear or exponential, so you have a lot of control over there. So then EventBridge has a pretty simple retry behavior. It essentially tries to deliver the events for up to 24 hours with some sort of exponential back off. Any failed events actually at this point are lost. It's very unlikely this is going to happen because most of the services that EventBridge delivers to are other AWS services. So it's unlikely that, say, the Lambda service or the SQS service would be down for 24 hours and then it wouldn't eventually deliver it there. And then this is an important thing too, is that once the events are accepted by whatever that target service is, then all of those failure modes for that target service are used. So for example, if EventBridge triggers a Lambda function, once the Lambda function or the Lambda service accepts it, then it's actually stored by that Lambda service, and those are invoked asynchronously. So the last thing sort of that we'll talk about in this is this idea of step functions. If you're not familiar with these, they're state machines, which allow you to do orchestration workflows. This is an example by Retry, who put together a Saga pattern using a step function or step functions and Lambda functions. And essentially what a step function is it allows you to create these really complex workflows with all kinds of guarantees and retry policies. So the Lambda functions themselves will all get invoked synchronously, which means that if that function fails, you want to bubble that right back up to the state machine, because the state machine has this concept of retriers and catchers, and it allows you to handle all these complex patterns. And that even sends back like an error name that you can use to do conditional error handling. So let's say it's a timeout error. Well, then we know we need to retry it maybe. But if it's some sort of a syntax error or something else happens, then we know to maybe raise a different type of flag or something like that. And what's great about these two is that you have a lot of control over the retry policies. So how many seconds it takes, how many times you want to try it, that back off rate, and so forth. So I'd be remiss if I didn't mention that the AWS SDKs that are available for pretty much every programming language and runtime that's available, they also have built-in automatic retries and exponential backoff. This is something that I was always nervous about using when I needed to guarantee that a message made it into an SNS queue, for example, or an SNS topic or an SQS queue. And what I would do is I would write my own retry logic on top of the retry logic that was already built into the AWS SDK. I've come to realize that this is not necessary. This is an eye chart here that shows you just an overview of the different SDKs and what the retry and connection timeouts and socket timeouts are. There's more information about this if you're using any one of these services or any one of these SDKs, go check it out and figure out exactly what the retries are and so forth. But I'll guarantee you do not have to write your own retry logic if you're writing code either from a mobile application or a Lambda function that's connecting to any of these services that are using these retries, that are using the SDK. Okay, let's get into some of the more fun stuff. These are some error handling patterns. So the very common sort of strategy that we use when we are doing heavy reads is to do something like a caching strategy. And so let's say we want to have an API gateway, calls our Lambda function, we want to pull data from RDS. The problem with this is that, again, RDS will only scale so much where our Lambda functions may scale infinitely. So one way that we can build in some resilience here and lessen the burden on our RDS cluster is to put in a cache, right? So we use Elasticache, for example, and we check that first. If we get a hit, great, then we can send that right back to the client. That relieves that pressure on the RDS service for us. If we get a miss in this example, then what we want to do is query the database, pull the data back. This is not a write-through cache, so we have to manage that ourselves, write the data into Elasticache, and then respond back to the customer. So a couple key points here is that we only want to make new connections on misses. We want to make sure that we set low TTLs. We don't want our data to be stored in the cache for too long. And we want to make sure we include the ability whenever data is updated that we can sort of simulate a write-through cache so that we can change, we can make sure we invalidate those keys that store stale data. Just one thing too is that you're probably saying, okay, hey, I was told by my computer science professor never to put a cache in order to sort of mitigate the or to cover the weakness of a downstream system. That is potentially true. We still want to make sure we size our databases correctly, that cluster can handle. If you expect 1,000 concurrent users, we want to be able to make sure we have 1,000 connections that are available to us. But what's nice about this is that if that database does hiccup, then, and we've got a lot of, we've got a nice warm cache with a lot of, active data in there, then that's just another strategy we use so that if that database has a hiccup or something happens or it gets overwhelmed, we get some sort of spike. These are those temporary things where we can add that level of resiliency and make sure we don't lose all that data or lose the customer and still provide them with something that's interesting and usable. So this idea of buffering events for throttling and durability, so that was, the last one was more about read-heavy applications. If we're looking at write-heavy applications, one thing we can do is simply put an SQS queue in between there. This will connect to that SQS queue, act back to our Lambda. We can reply back to our client and say, hey, we got all the, we've captured your request. This is great for things like webhooks or any sort of high velocity, spiky traffic. So the SQS queue then would be attached to a Lambda that we'll set a concurrency on, and that will limit that throughput so that we don't overwhelm that RDS database. We'll pull the Lambda function, pull the SQS queue, write the data to RDS, and then tell the SQS queue that we've got it. Meanwhile, the client has already been disconnected and went on their merry way a long time ago. If this fails for some reason, then, and it fails enough times that we want to put it into our dead letter queue, we can send that right into our dead letter queue. So a couple key points here is that SQS adds a tremendous amount of durability. It's very lightweight. The likelihood of SQS being down and not being able to capture a message is very, very low. And then being able to throttle the Lambda function gives you the ability to reduce that downstream pressure, which is really important when you're building hybrid systems, and not all of your components are as serverless as we would want them to be. And then finally, that idea of that DLQ. So those failed events get stored. We can inspect them later on, replay them possibly, and so forth. Now, one of the things you might notice here is that we actually don't need this Lambda. We can use something called service integrations, and we could write the data directly into the SQS queue since we don't necessarily have to do any transformation. And then we could use that Lambda that we've got throttled downstream, and we could actually use that to decide whether or not we want to maybe reshape it before we write that data into RDS. But that way it's disconnected. It's, it makes it a little bit faster and get rid of some latency and lower our costs a tiny bit. All right, so the circuit breaker pattern, this is one of my favorite things in distributed systems. Essentially, if we had a nice happy path, right, we call the Stripe API, responds back to our customer, everyone is perfectly happy. But like we said earlier in the presentation, everything fails all the time. So what do we do if this happens? All right, so rather than us calling the Stripe API directly, we put a status check in between here. And essentially, this is just going to check a DynamoDB table or maybe Elasticache, and it's going to see whether or not the circuit is closed. When a circuit is closed, electricity flows. So we go ahead and we make a call to the Stripe API. If that succeeds, great. We return the data back to the Lambda function. We reply to the client, say, hey, everything is great. But if it fails, then what we want to do is we actually want to try to increment the failure count so that after a certain number of failures, and again, this is based off of the velocity of the data or how often you're calling the API and so forth. But if it reaches a certain threshold, right, and when it fails, we can just respond to the client and say, sorry, it's not available right now. And by the way, the client could be, say, an SQS queue or something like that where, that there would be a redrive or the ability to retry these failed events. But once it gets to a point where it's failed enough times where we say, that API is just not responding, then the status check is going to tell us actually that our circuit is open. We've switched the light switch off, and now we can respond back to the customer immediately saying, hey, listen, we can't connect to this API right now. And the reason why this is great is because we are not doing anyone any favors by pounding a Stripe API or pounding an API and potentially DDoSing that system because we have all these exponential retries built in or things like that. So we want to be careful about that and make sure that we're good, net citizens or whatever, netizens or whatever they call them, and make sure we don't overwhelm other resources across the internet because that's the worst thing that can happen. So what we do want to do, though, is periodically check and make sure that that circuit is, or that API is coming back up. So we would do what we call a half open. check the Stripe API. If it fails, fine. We just keep on going and returning errors. But then every once in a while, let's say that it eventually succeeds, then what we would do is update our caches, let them know that we are now in the closed state, and then the next time the request comes through, we are now flagged as closed. So a couple key points here, because people might ask themselves, like, I don't want to be called, especially if I have a high velocity system, I don't want to be calling DynamoDB, hundreds of times a second. Totally agree. So what you want to do is in each one of those functions, even if they're parallel and you've got 50 concurrent functions running, you can still cache your cache. So if you have to check the API, if you're calling it that many times, if you have to check the API 50 times before your Lambda each one of those Lambda functions realizes that it should stop sending messages, that's perfectly fine. I mean, again, this is about mitigating things and backing off as opposed to just being 100% accurate. You want to make sure that you use that reasonable failure count, right? You don't want, if you get 1,000 requests per second, you don't want to fail after, say, 2 requests, right? We maybe want to fail after 10 seconds of the system not working or 30 seconds of the system not working. And then also we need to make sure, going back to the idempotency thing, we understand idempotency. Super important, because with this method, it's possible that API actually received the message just fine, but something got lost in translation on the way back. The response got messed up or whatever. So it's possible that you're going to keep submitting things over and over again. Stripe API, simply because I call it out here, has a really cool feature called an idempotent ID, where you can send in some unique ID or a hash of the event or something like that, and it will make sure that it doesn't repeat it on its side. So that's great for not reprocessing credit cards or processing a credit card multiple times. So this is another one that I mentioned earlier about this idea of using EventBridge. So if we have a service that generates some events and we want to have a Lambda function that will process that event, and do something, maybe it's adding data to Salesforce or Marketo, or sending out some emails, or it's doing something that is peripheral and doesn't have to be in sort of that main synchronous path of the application. What we can do is we can use a processing Lambda. If it succeeds, then we send it to EventBridge, back to the same bus or a different bus or whatever we want to do, and then send those on to their merry way to whatever the other services might be consuming it. But if we get a failure here, we also want to use that on failure in Lambda destinations and write that into EventBridge as well. And then we can create a rule so that anytime there's some sort of permanent failure, maybe it's a it's a bad message or whatever it is, we can inspect that information. We can write rules that would route those to this permanent failure. But there is the possibility that some of these things might fail because it was a downstream issue or whatever, and we maybe want to replay those. So we have a lot of information in that on failure event that goes into EventBridge, so we can write rules that would give us the ability to reprocess retryable failures. And so we would use something like a delivery delay here, meaning that we would say don't expose this message in the queue for, say, another 5 minutes or 3 minutes or whatever we want to do. Again, depends on velocity and how your application is designed. But then you can have a replay Lambda with some throttling in place, and you can use that to call that processing Lambda asynchronously, and it will run through that loop multiple times until things get processed correctly. So just kind of a cool pattern. There's really interesting things you can do, but this builds in a lot of resiliency, builds in that retryable capability for you. It looks a little complicated, but it's actually not. It's not that complicated to handle, and I really like using this pattern because it makes not having to worry about certain retries, just kind of handle them for you. So that's good. All right, so quickly I want to go through decoupling our services, because this is just an important point about building distributed systems and adding that resiliency in there and handling failures. So SNS, if you're familiar with this is a pub sub service that AWS has. You would send asynchronous requests to this. You get a response back that says, okay, we've gotten the message, and then your client can disconnect like we talked about. But SNS can actually act as its own little event service, and you can trigger SQS, email, HTTP, SMS messages, and Lambda functions all, and have it send them to multiple ones. So you can have multiple subscribers. If any one of those fails, you've got that SQS capability we talked about. And a couple of things about this is SNS is great, has a very well-defined API. So if you're thinking in terms of microservices, and so forth. That API is not going to change. This helps decouple those downstream processes, and it allows for multiple subscribers with message filters. SNS has sort of become, it was sort of a staple in serverless applications for doing message communication, event messaging. We're going to use EventBridge for that now, but SNS still is great for very, very high throughput applications like sending emails or SMS messages or anything where it's got to send a lot of events and it's got to do a massive fan out. SNS is still a great service for doing something like that. But now with EventBridge, we can pretty much do the same thing. We can send a event to EventBridge, get a message back. We also get the event ID, so we can actually track that through if we wanted to. This can also call SQS and Lambda functions, but Amazon EventBridge actually allows us to do things like call step functions. We can send messages to other EventBridge. There's 16 other things that it can do. And each one of these, again, has this message rule or this filter that it can use in order to determine, based on the event in EventBridge, which functions or which services get invoked. So a couple key points here. Multiple subscribers, rules and patterns can be used to determine which ones get triggered. You can forward events to other accounts, which is super helpful if you have like maybe different microservices and different accounts, or you've got certain stacks that are separated that way. And then, like we talked about, you get that 24 hours of automated retries. So if we were to put this in the context of an actual application, let's say that we have maybe an e-commerce application, an API request is made to submit an order, and the Lambda function processes that. We would go ahead and send that into EventBridge. EventBridge would reply back, and we would then reply back to the customer saying, hey, we captured your order. Almost every e-commerce system out there now, you will basically see that it says, okay, we've got your order, and then you get an email later on to let you know that it was processed or accepted. So what we can do here is then we can actually build a completely different service. Let's just call it our Lambda or our order service. And what this is doing is this is just capturing our order data. So we would set up a rule, and that would be specifically for this order service. And anytime a message came in that met that certain criteria, it would put it into an SQS queue, would have that extra durability there. Our Lambda function can use that to chew through that queue and make sure that data gets written to RDS. The great thing about this pattern right here is I've captured the user's order. If all of the rest of my systems go down, it doesn't matter. I've captured that user's order, and even if I have to process it 5 days later, I still have it. And so now that SQS queue is going to add that resiliency and that durability for me. That Lambda function is going to be able to pull that and minimize the impact on the RDS cluster for me. And if that RDS cluster is down, then I can just wait. And even if my SQS and DLQs into the RDS database and that database fails and it goes down, you're not collecting orders. But what's great about this is now let's say we want to build an alerting service. So we can set up another rule that listens for the same type of order submitted event or whatever it is. We use the same type of thing. This time we're calling the Twilio API. We can throttle the Lambdas. We can queue it. We can build, say, a billing service that's going to actually contact Stripe. And then we set up another rule that sends the data through. So all this stuff works, and each one of these individual services are independent, and they are not going to butt up with one another, and each one can fail. The order service and the alerting service can be down, and we could still end up billing the credit card, but we still have the data captured in other places. And then you can set really complex patterns. So this can just be something like only accept ones with the detail type order complete. But you could also say, listen, we're not going to build something unless the value is over 0. So maybe you're giving away certain free ebooks or something like that, and so we don't actually have to bill them for it. Then you can build that logic right in through your EventBridge rules. So a couple key points here is that you can filter events to selectively trigger services. You can manage all that throttling, quotas, failures. All that stuff is managed on an individual per service basis that can be separated by team. Everybody can use their own services. It really is nice to use that method. And then again, if you're using use Lambda destinations if you're ever triggering things with asynchronous invocations. All right, so a couple final takeaways here. Just be prepared for failure, because in the cloud, everything fails all the time. Just accept it, right? And then make sure that you utilize all these built-in retry mechanisms of the cloud. They're there because they're great and they work really, really well. So learn them and utilize them. Understand all the failure modes, right? So we want to make sure the biggest thing is that we want to capture data. We want to make sure we have the data. As long as I have the event that you submitted, it doesn't matter if everything breaks after that. I can retry that. I can inspect it later. But if you lose the data, then all of that goes away. So capturing the data is the most important thing that you can do in a distributed system like this. Make sure you buffer and throttle events, right? So distributed systems are notoriously unreliable, and that's okay. But we want to make sure that, one, we don't overwhelm downstream systems, and we want to make sure that we have some level of resiliency, like an SQS queue, so that if there is a failure, that we don't lose those events. And finally, embracing asynchronous processes to decouple components. So that is my biggest takeaway, I think, for all of this is just get comfortable with this idea of not having to process everything immediately. Make sure that you simply capture the data and then send it off to somewhere else that can process that. That adds a ton of resiliency, and it just makes it a little bit easier to understand, and build those other downstream pieces of your system, and make sure that you're sort of tailoring each type of invocation and action against those. You're tailoring that to each individual system, and you can get really, really granular there. So that's it. So I appreciate everyone listening to me. These are just a couple of things that I'm working on. So my blog is jeremydaly.com, serverlesschats.com for the video podcasts. It's YouTube and all of your favorite podcatchers. Offbynone.io for the newsletter. I just am almost ready to launch V0.2 of the DynamoDB toolbox. If you're working with DynamoDB and Node.js, check this out. I think it's going to be awesome. Lambda API is another service. I got some other ones at GitHub, and make sure you follow me on Twitter. And that is it.
Awesome. Thanks a lot for that, Jeremy. Now it's I've disabled the event mode, so if anyone has questions, you can either add it to the chat, or you can just unmute yourself and ask them. Let me see if I can see the. So I know there were a couple of questions coming in earlier on, which is sort of talking about if there's any chance of people getting hold of the slides. Are they available anywhere?
They are not, but I gave this talk, similar talk at Serverless Days Nashville, and that is available. The video for that is available. I think I posted the slides. So if I didn't, you know what? If you follow me on Twitter at Jeremy_Daly, I will post the link to these slides.
The next question was whether for some of these, are there any sample resources? So I know when you've talked about things like microservice patterns, is there anything in GitHub or similar that allows people to sort of stand them up and see them working?
Yeah, so there's actually a team over at Liberty Mutual who is building this thing called CDK patterns, and they've taken. I wrote a blog post a couple of years ago called "Serverless Microservice Patterns for AWS," and if you go to my blog or search for it, you'll find it on Google. And what it does is it outlines a lot of those different patterns. Things like a streaming, doing kinesis streaming and step functions and FIFO queues and some of those other things. Those are all outlined there. There's not code samples for those, but other people have implemented some of those. And if you look around, you should be able to find them. I'm actually in the process now of trying to revamp that whole thing and provide some of those samples because everyone asked me for those. So I do have some other patterns on my website where things like throttling lambdas, DLQs, or things like for quotas, that kind of stuff. Some of those things I do have code. If you look around my website, you should be able to find some of those.
Well, there's a very specific one in terms of, do you know if there are any limits on how many rules can be applied to EventBridge?
I think there is. Is it? No, I don't think there's any rules. There's a limit of 100 something. There's 100 event buses, I think, per account. But the number of rules, I think it's unlimited or, infinite to. I'm sure there's some upper limit, but you can write as many rules as you want.
So the next question, there was a 40-person enterprise with about 12 developers migrating a monolith to serverless. So I'm the only one who already works with serverless, mainly SAM, starting to use Amplify. So which do you think would be the better framework to start spreading serverless on the team? Because the choices are sort of Amplify, SAM, serverless framework. Is there any that you particularly use or recommend?
Yeah, so I'm a huge fan of the serverless framework, and I will tell you that if you are trying to take a monolith and bring it into serverless, Amplify is probably not what you want to do. So Amplify is great. It's like a bootstrap, a quick greenfield application, gives you everything you need to. I know they're building more in to allow you to do other things as well. It is an incredible framework, absolutely. But it is, I think, very much so tailored for sort of bootstrapping an application. So if you are, a greenfield type thing. So if you're taking a brownfield application, you're trying to break that up. I mean, again, I love the serverless framework because I think it's just this really nice abstraction, and it also gives you all of these really great plugins, right? So with SAM, which is also great. I mean, I like SAM as well, but there aren't plugins for SAM. You have to write, custom resources and things like that, which basically just means you end up writing Lambda functions that do something in order to deploy Lambda functions and do some of that stuff. So a lot of really great developers for the SAM stuff. Obviously first-class support for CloudFormation and that kind of stuff. But I love serverless framework. I started using it when it was still JAWS back in 2016 or something like that. So it is. I would suggest that it's very easy to get started with. Tons of examples out there. Lots of very, very large developer community around that, and I think that, in my opinion, will give you the most flexibility.
Okay, awesome. The next question is around Lambda destinations. Mm-hmm. So it's great because you have a context of the failure, and from what you're saying, you should be relying on a Lambda function to retry failures. So can you still see a need for a DLQ at some point?
Yeah, so actually what I consider on failure, what on failures to be is just a better interface to control how DLQs work. So if you are, so the problem with DLQs just in general is, let's say I get an event and it fails, then that event's going to write into my SQS, for example. If I go and I look, I'm just going to see an event, and unless there's something obvious about that, that stands out, I have no idea why it ended up in that event ended up in that queue without going and inspecting the log files for whatever processed it. So it could be a bad character or something that the system didn't like, or some tiny piece of JSON that wasn't formatted right that I'm not going to be able to see just by looking at it. So what on failure does is it just allows you to have more control. It adds all that extra context. It captures the stack trace and information about the ARNs and some of this other stuff, as well as the original event. So you also get that original payload, but then you can take that and decide what to do with it. If you just want to capture it and you don't want to reprocess it, you just want to capture these events, just point it to SQS and use it just like you would a normal DLQ. You just get more data there. I like the idea of reprocessing these things with a Lambda function after the fact. So what I wouldn't do is route SQS. I wouldn't route an on failure directly to another Lambda function. I think that wouldn't make a lot of sense. Again, durability, resiliency, right? We want to make sure that we capture whatever that failure was and have that stored somewhere. SQS is perfect for that. The only reason why I suggest sending that into EventBridge, for example, is because one of the things you would do with EventBridge is have SQS queues probably attached as rules that would capture those failure events if something happened there. So you have the ability to sort of manipulate the way, rather than just sending it right into SQS, you have all these other options to sort of route the data or understand the failure and put that into the correct sort of downstream or system where you would be able to reprocess or inspect it. I mean, one of the things you could do is if you really wanted to write it to a Lambda function and then say write that into DynamoDB, you wanted to write all your errors into DynamoDB or dump them into S3 or something like that, you could do that. I still would suggest putting SQS in front of all of that. EventBridge to SQS is perfectly fine. Same thing with SNS to SQS, perfectly fine to do that. But get it into SQS somehow so that you have visibility into that queue and you have that durability.
Oh, fantastic. Next question was whether do you have any serverless patterns for dealing with idempotency?
Yeah. So serverless. So idempotency is one of those things that is not unique to serverless in any way, shape, or form. It's a little, sort of unique to, I guess, distributed systems in a sense. It comes into play more. So there are a bunch of different things that you can do, and if you look up idempotent strategies, you will find a bunch of things. Oftentimes, what we do is if we're writing data into an SQS queue or writing data into some system, it's typically hard if there's no check there for uniqueness, right? And so if we're writing an event into SQS, we're not going to have uniqueness there. So instead, what we want to make sure we do is on the other side of that, on the consumer, we want to be really aware of the uniqueness of that event. So one thing we can do is that when we're reading off an SQS queue, we're always going to get a unique message ID. And if it's the same message that is processed more than once by your downstream service, then you'll get the same message ID. That's typically not the problem. What typically happens is, and that can happen, but usually you have this other problem where you submit the same event to SQS multiple times. So now you have two separate message IDs, but the same data. So depending on how your data is structured, then it's really good practice to take some sort of hash of the data that doesn't change, right? So maybe the date might be, the date might be different. Maybe you only want to take the first part of the date, or maybe, cut out the seconds or something like that. But take some bit of that. Take the payload itself, take some other bits of information, calculate a hash with that, and then use that as that item potency key. And you can write that into your own database. So if you're using DynamoDB, for example, and you're consuming off of a queue and you're writing into DynamoDB, use a condition expression and say, as long as this ID doesn't exist, then don't write the data. And then that way you can reprocess that. If you've got 100 of the same event stuck in your SQS queue, you'll process 100 of those, and the only one that will actually write to DynamoDB will be that first one. So there's all kinds of strategies like that. They're available all over the web, but it's more about thinking about that and knowing that can happen. And then I think with a little bit of research, you'll find all kinds of ways that you can mitigate it.
Okay, and then another one was how much use, when you've been implementing these sort of patterns, have you found of services like X-Ray or things like RDS proxy?
So I mean, things like X-Ray, I don't run those in production usually because, I will sometimes if I'm really trying to debug something, but for the most part, it just runs a sample. It gets kind of expensive. To me, they're helpful when you're running like on a staging environment and things like that, if you want to try to trace some of those things, because you want to kind of capture every invocation. I actually find services like Epsagon or Thundra or any of these services that do distributed tracing for you to be better than X-Ray. I mean, X-Ray works really well, and it will give you some of those performance metrics, but it doesn't really do the distributed tracing the same way that these other tools that are sort of purposely built for do that. In terms of things like RDS proxy, I haven't used it yet, mostly because I had written a library called Serverless MySQL that handles some of that for you. I was under the impression that my package would become obsolete once RDS proxy came out. RDS proxy tends to be a little bit expensive. It's not ridiculously expensive, but it's also not a silver bullet, right? So it will help mitigating some of the connection pooling issue for you, which is a major concern when you're running Lambda functions that have to create a new connection to your database every time. Because they're ephemeral, because they're constantly recycling themselves, you're going to run into zombie connections all the time. The RDS proxy will handle a lot of that for you, but you still have throttling, connection issues, all kinds of things like that, which the library that I wrote does that. So I tried RDS proxy just to kind of experiment with it, but then kind of digging into it deeper, I felt like it wasn't necessarily going to solve the problem that I needed it to solve. But I do think it's a quick out-of-the-box solution that you can apply to any language. Mine, mine's node-based and only works with MySQL. When now you can use RDS proxy on MySQL, you can use it on Postgres, and of course you can use it with any language because it's language independent.
And then a last question just scraped in here. So since a browser HTTP call is very likely to fail, it appears we need to push a lot of the retry or user notification intelligence back to the browser JavaScript. Is that right, or are they missing something?
Yeah, well, I mean, you're not going to get a lot of failures making an HTTP call. I mean, that's the failure that I think I'm talking about when it comes to networks is the fact that there are failures. I mean, it's just, again, packets get dropped, things happen all the time. It's about understanding and building in ways that if that happens, you can mitigate those. If you're building a single page app or any application that's calling API Gateway, for example, the failure rate on that is going to be tiny. I mean, tiny. I mean, likely what's going to happen is it's going to be some connection issue locally. Your Wi-Fi dropped down or something like that happened where you weren't able to connect. So you do want to build some bit of resiliency onto your local into your local JavaScript that is calling these services, especially if you're using I should take a step back. If you're using the AWS SDK, you really don't need to, because that has those retries built in for you. But if you're just calling maybe your own API, or you're writing connections to a WebSocket using API Gateway or something like that, building some retry logic in there is just, I think, standard practice. It's no different than what you would do if you were connecting to containers or a traditional, Apache web server or something like that. That's still just good practice to make sure that if something fails, you have some bit of retry logic in there. But again, the failure rate would be infinitesimally small.
Cool. And finally, there were a significant number of comments in the chat just talking about what a fantastic presentation it was, and just thanking you for that.
Thank you.
So
I appreciate that.
So yeah, there definitely was a huge amount of content to try and digest and get our heads around. So we've been recording the talk. So it will be made available in the next few days on our sort of South Wales Meetups YouTube channel. So people keep an eye on the Meetup page, Twitter handle for this user group and Serverless South Wales. So we've got some talks coming up from the likes of Jan Chouet and Alex Debris, which we'll be announcing shortly. But if there is anyone that's interested in giving a talk, if there's a topic you'd like to learn more about, please let us know. So with that, just a huge thank you again to Jeremy for giving up your time. Follow him on Twitter, subscribe to his podcast and his newsletter, keep up to date. Thank you very much to everyone who's given up their time to join the meetup. Stay safe, and we look forward to seeing you all soon.
Thanks, Matt.